Today we will be starting a new session on the course line commutated and PWM rectifiers. So now we have understood what is the controller structure, and now we are going to see or find out what is the small signal model of the voltage source converter. Okay, for this we have to again rewrite the equations which involve this dq or the DC quantities at a steady operating point or the quiescent operating point. Okay, so these are the equations which we have already seen. I think equation number 4 from some slides before. Now when we do small signal modeling, the method is that there is a steady operating point over which we give a small perturbation to the input variables, and we see what is the impact of that perturbation on the output variables. Okay, so which means on a DC quantity, which is a steady operating point, on a DC quantity we give a small AC perturbation. Okay, and so then we find out what is the transfer function of those between the output and the input variables, okay, over that small perturbation, small AC perturbation. Okay, and then we can apply the linear control system theory to design the controllers. This is what is very well known in many branches of engineering, including power electronics, and this is what we will follow here. Okay, so how do we do this for these equations? So you can see here what we have done here. V con D, we write the equation as a DC and a small AC quantity. Okay, so V con D is, this is the DC part and here is the AC part. Okay, where the AC perturbation is much smaller in magnitude as compared to the what is the DC operating point. Okay, so as if like you are so with respect, so V con D is here. Okay, it is varying, okay, with time. Okay, so this is the steady operating point over which we give as if like a small AC perturbation. Okay, a small AC perturbation over, this is the AC perturbation here, give a small AC perturbation, right? So we give this to all the variables. Okay, and we will then find out the transfer functions. So so we do this exercise for V conf Q, we do the exercise for IGD and IGQ. Okay, where these conditions will be all satisfied. Okay, and we also do the same thing for the V grid. Okay, the grid voltage. Now let us put this back, okay, into the previous equation and see what happens. So if I put it back, so the converter voltage is now written like this, the Ri drop is written like this, L di dt is written like this, omega L is written like this, and V grid is written like this. Okay, now when we are trying to develop the small signal equation, we will only take the AC terms here. Okay, the hat terms. So we collect all these hat terms here, and so we see that this is the equation of the VSC, is the small signal equation of the VSC in the D axis reference frame. All these are D axis, so you can see here these are the D axis. Okay, so this is the cross coupling term. Okay, these are the D axis term. So this is the small signal equation of the VSC in the D axis, and similarly we can find out the same exercise we can do, and we can find out V conf Q, okay, like this way, and this is the small signal equation of the VSC in the Q axis reference frame, right? So we get the small signal model. Okay, and let us now apply the Laplace transform to these equations. Okay, right, because we are eventually going to design the controllers and we have to do it in the S domain. So we will apply the Laplace transformation to these equations, and so we can write, so this this is the equation which we have written in the previous slide, and we can simply convert it into the Laplace domain. So vcon ds, so what happens, L d dt will become Ls igd, right? And this is how the equations will now get transformed, right? So if we collect it and rearrange this equation, what happens is vcon d hat s means the vcon d plus omega Ligq, and v grid d is r plus Ls times igd. Okay. Similarly, you have this vcon q similarly coming. Okay. So this is the equation in the for the small signal equation in the S domain. So let us diagrammatically put this. Okay. So these two equations you can write it in a diagram. Okay, or you can draw it in a diagram. You can see here these are the two outputs. This is expected, right? So we are going to control the igd and igq by using this vcon d and vcon q. Okay, we are going to control through the converted voltages. So these are the input and output, and what is present here is this cross coupling term, right? This cross coupling term is there, and there is a addition of the v grid d here. So this is basically the plant model. Okay, the plant model has these r plus Ls terms which is coming from the filter, and there is a cross coupling term which is here, and there is a v grid d coming from here. Okay, but what is most important is that this r plus Ls is something which is very attractive to us. Okay, it is showing that the voltage source converter, okay, can act as a simple RL circuit based on the filter, provided there are certain conditions. For example, here we have taken certain assumptions. What are the assumptions? Number one, we have neglected the effect of the dead time. More importantly, we have not taken any delay in the system, right? Where are the delays? For example, when you give a pulse output from the microcontroller, and when the switch turns on, there is a gate driver circuit, and there is a finite time required by the MOSFET or the IGBT to turn on. So there is always a delay between when the controller gives the output and when the actual switch gets state changes from 0 to 1, for example. So there is always a delay, but this delay we have neglected, and there is a reason for this, why we have neglected it. The reason is modern day power electronics, okay, and with the modern microprocessors, they are very fast. Okay, for example, these nowadays MOSFETs or even silicon carbide MOSFETs, they take hundreds of nanoseconds to turn on. Okay, less than microseconds, much less than even less than hundreds of nanoseconds. So they're very fast. They turn on and turn off very fast. In a similar way, the microcontrollers also, the present day microcontrollers can easily work in say 100 or 200 megahertz. So the the delay in the whole processing system and the delay in so the switching frequency of the devices are very high nowadays. Okay, it is very common for the switching frequency with silicon carbide MOSFET. Very frequently we say 50 kilohertz or 100 kilohertz switching frequency. So all these delays in the system have now become very, very small. So our assumption that these delays are negligible with respect to the controller design is something which is very reasonable and is a quite accurate representation of the system that modern power electronic systems, modern grid connected VSCs are operating with. So with that assumption, or with those necessary approximations, our model becomes very simplified. Okay, So the model in that has this precisely this R plus LS term. Okay, so which means that the which means that uh, the response of the VSC is primarily controlled by the filter R and L terms. Okay, whatever is the delay is primarily because of that. So therefore, if but of course there is these two terms. Okay, these two terms are problematic because this is the cross coupling term which we have here. Okay, and we have already seen that it degrades the current controller performance, but we have seen in some of the previous slide, you can see here, this one here, remember we have already added this term here and this term here. Okay, we already added these feed forward terms, right? This was added precisely to take care of those cross coupling terms, okay, and the V grid T. Okay, so we have already added it in the controller so as to take care of the cross coupling term inside the plant. Okay, and this is actually works very nicely in the actual system. So if you see here in the model, although we have these cross coupling terms and this V grid D, we are actually taking care of it inside our controller through the feed forward terms. And so therefore we actually can neglect or we can say that okay, we can therefore simplify our controller design, which I will show in the next few slides. Okay, so this whole thing now, the converter is now represented as a block or the plant in the control diagram, and here you can see that this is the small signal DQ model of the VSC. Okay, so you can see here, this is the input, here is the input, these two are the inputs, and here is the output. Okay, so this is the small signal DQ model. So when you now introduce the small signal model in the overall control diagram. So here you see this is the small signal DQ model of the VSC. Okay, now in the whole control diagram, you see we go back to the previous one and see IGD star and IGD. Okay, IGQ star and IGQ. Okay, this is what we had seen, right? Here it is, this IGD star and IGQ star. Okay, these were here. Okay, so this is the whole control system, and then there is a sensor gain here. Okay, this is the feedback because we have taken a feedback, and here is the feedback, IGD coming back here, IGQ also feedback. Then there is a PI compensator, and here is the feed forward terms. Here are the feed forward terms which are taking the effect of this cross coupling terms here, right? And so this is the overall control structure. Okay, the plant is present, and with this one we can actually design the compensator values here. This KP and KI values we can design inside this one. So this is the overall control diagram. What is important here is that once once these feed forward terms completely cancel the effect of the cross coupling terms here, okay, it can be nullified by the controller. Okay, so then we can actually take these two out from the control diagram. Okay, but for that an accurate knowledge of the L is needed for adding the feed forward terms. Okay, we need to know what is this omega L. L actually sometimes vary during the during the operation because of saturation. But accurate, if you know the accurate knowledge of L, then we can add this feed forward term in the controller structure so as to cancel the effect of the cross coupling term inside this model. Okay, if we can do this very nicely, then what happens is that we have a perfect cancellation of the cross coupling term, and therefore the whole resultant controller diagram looks like this. You can see here, right? We have taken out, or we have removed those cross coupling terms, so the plant becomes 1 by R plus Ls. There is this gain Vd by 2, which is coming because the modulation is the VSC, whatever VA star, VB star, VC star we generate, it gets amplified by Vd by 2, M Vd by 2, if you remember, M Vd by 2. And then there is this PI compensator. Okay, so here is the PI compensator, right? And this is the reference, and this is the actual D current. Okay, so as I told you, the voltage source converter behaves like a current controlled voltage source converter. So we give a current reference. Vector controlled VSC is a current controlled VSC. So this IGD star comes from PG star, how much active power I want to give, and this comes from QG star, how much reactive power I want to exchange. Okay, so those PG star and QG star controls what is IGD star and IGQ star. And then we have this PI. Okay, and we have the feedback. Of course, we get the feedback from this one. The feedback comes here. Then we have the error here, which is given to the PI compensator, and then we have Vconv hat D and Vconv hat Q, which gets multiplied by Vd by 2 so as to get the actual voltages here, and those actual voltages is scaled down by 1 by R plus Ls. Okay, because now here we have completely cancelled the cross coupling, the effect of the cross coupling term. Okay, and this is, both of them look like a perfect second order system. Okay, this can be, because this plant model is a first order system. Okay, so we can actually design the compensator, that additional pole and zero. We can nicely work on that so as to make the whole system behave like a second order system. Okay, which we know from our control system theory. We know how it operates, a second order system. So therefore, the whole of this aim of the control system was to find out that whether what is the plant model, and fortunately by adding these feed forward terms and doing the mathematical jugglery, we found that the plant can be treated as a first order R plus Ls, 1 by R plus Ls, and then we can do we can add a PI compensator to get a second order response, so corresponding to what is the IGD star. And so you can understand that by doing several approximations and some assumptions, we have actually been able to reduce this complex system into a nice second order system. Okay, this was actually the aim from the beginning. We want to make sure that this system behaves like a second order system, so that because we understand the second order system very well. Okay, so this was the aim, and we have been able to do that. So here now you can see the transfer function looks like a second order system. So you will see IGD star is something like this equation. Okay, this you can just see from the diagram and can find it out yourself. So then we can actually have a how much is the zeta, the damping coefficient, okay, and how much is the bandwidth and all. So these are the values which will come when we compare with this standard second order system equation, s square plus 2 zeta omega ns plus omega n square. Okay, suppose we have a filter which we will choose like L equal to 0.04 millihenry and R equal to, so like this, and we choose the one is like 2 pi into 200, and so we get these values. Okay, Ki is so much and Kp is so much. So this is one way of actually designing the closed loop control of the VSC. But we will not stop here. We will actually do another way of tuning the regulator using a per unit system. Okay, we will draw the Bode plot and then tune the controller parameters nicely, which we will take up in a next class. But what is important here from this discussion, the discussion whatever we have covered is there are several things that are important in this small dynamic modeling. We first understand that this dynamic modeling, from the dynamic modeling, we are basically treating the whole of voltage source converter into this D and Q axis circuits. Okay, as if there is a D axis circuit, and the D axis circuit controls the active power. The Q axis circuit controls the reactive power. So that is the first understanding that we get. Okay, the second understanding that we get is that they are first order system. The model, the plant model is not exactly first order system. The plant model is something which has a cross coupling term, but in the controller we do some jugglery, we add some feed forward terms so as to modify the whole system and make it behave like what I have shown in the current slide, like a second order system. And this second order system makes sure that whatever is the IGD star and whatever is the IGQ star, we can actually get it from like as if like we are dealing with a second order system. There will be certain overshoot, there will be a certain damping, okay, and a certain settling time which we know, okay, from our control system theory. So and also we understand that when we work with this is called a grid vector control of grid connected VSC, and in this we understand that the voltage source converter is treated like a current controlled voltage source converter. Okay, it injects P and Q with the help of a current source as if it is behaving like a current source. Okay, so it's a current controlled voltage source converter. Okay, so with this all these things we conclude today's lecture. So with this one we conclude our session, and I would like to see you once again in another session on the course line commutated and PWM rectifiers.